We can also use the chi-squared statistic to allow us to test whether or not we have things that are independent or not. So a contingency table is what we're going to use here. A contingency table relates to qualitative variables. We're going to use these when we perform these tests of independence and homogeneity of qualitative variables. So we're interested in determining whether the distribution of one variable differs depending on the value of some other variable. So if this is the case, that it does vary based on the values of some other variable, then that implies that variables are dependent. However, if not, then that would imply that they are independent. So here, when we're looking at determining whether or not two variables are dependent versus independent, our null hypothesis is that our variables x and y are independent. Use capital letters for these. However, our alternative is going to be the opposite, that our variables x and y are actually dependent. So again, we're going to use the chi-squared statistic when we're trying to perform this test. And so similar to the chi-squared statistic, we're going to start off with observed values, and we're going to have to find our expected values. So here's an example. We want to know if some college majors require more studying than others. The National Survey of Student Engagement asked a number of college freshmen what their major was and how many hours per week they spent studying on average. A sample of 1,000 of these students was chosen, and the number of students in each category are given in this contingency table. So their hours per week were separated into these three categories. The different majors that they were looking at are all separated in these four categories, and so these are the observed values that we have. So let's just kind of go ahead quickly and calculate some totals for our rows and our columns. So here we have from the 0 to 10 hours per week, we have 345. From the 11 to 20 hours, there are 430. From the more than 20 category, there are 225. If we're looking at the humanities, there were 257 of those, 261 social science students. Business, there were 309. Engineering students, there were 173, and there were 1,000 total individuals in the sample. What we want to do is we want to perform a test that majors and the hours of studying are independent. We're going to use a very small alpha here, so 0.01. Hopefully this will give us something pretty strong. So let's just start off with our null and alternative hypotheses here. The null hypothesis in this case is going to be that the major or type of major chosen and hours of studying are independent. The alternative is going to be that the majors and the hours of studying are dependent. So all these little lines means just take the thing from above. So, okay, so we talked about how this is going to be a chi-squared test, which means we have observed and expected values. So remember that if we are assuming independence, right, so that is the expectation here. That is our null hypothesis. So assuming independence, D-E-N-C-E, then we were going to expect that, for example, the probability of being somebody who studies for 0 to 10 hours and is in the humanities. Remember, for somebody to be in both of these categories, you kind of think of this using the and symbol. If they're independent, what that means is that all we have to do is take the probability of studying for 0 to 10 hours and multiply it by the probability of being part of the humanities. And so how do we figure out what those probabilities are? Well, what we're going to do is we're going to use our totals that we found. So in this case, we'll take the probability of studying 0 to 10 hours, which is 345 out of 1,000, and multiply it by the probability of being in humanities, which is 257 out of 1,000. So when we multiply those together, we get 0.08865. But this is just what our probability is. So expected frequency is going to be found by taking this probability we just found out, 88665, and multiplying by the 1,000 people that we have. And so we should expect 88.665 people. And so what we can do is we can do this to create a table of all of our expected frequencies. So what we have is, what we're taking is multiplying the total for the row times the total for the column. We're dividing twice by this total overall, the grand total, but we're multiplying again by the grand total. And so really, when we take that, we just end up dividing by the grand total once instead of twice, because one of them will cancel out. So as we go to make these calculations, our expected frequencies will just be found by taking the row total times the column total and dividing by the grand total. So our expected table, again going 0 to 10, so we get very small very quickly, 11 to 20, and then greater than 20, versus humanities, social sciences, business, and engineering. Here we found our 88.665. If we want to use this formula to find the number of people who are in social sciences and studying for 0 to 10 hours a week, we'll take 261 times 345 and divide it by 1,000. So 261 times 345 over 1,000. Next we'll use, find a way to get these both on the screen at the same time. There it is. We'll use, just kind of keep going through this row of 0 to 10 hours a week. So business is 309. So we get 309 09 times 345 over 1,000. We'll end up getting, for engineering 0 to 10 hours a week, the 173 times 345 over 1,000. And we can keep it going. Then next we can do the 0 to 10 hours. So we should end up here. Everything in this row will be multiplied by 430. So 257 times 430 over 1,000. 261 times 430 over 1,000. 309 times 430 over 1,000. And 173 times 430 over 1,000. All right, one more row. We having fun yet? All right, so last row, we're doing this more than 20 hours, so everything's gonna be multiplied by 225. So we've got 257 times 225 over 1,000. We have 261 times 225 over 1,000. We'll have 309 times 225 25 over 1,000. And then last but not least, we'll have 173 times 225 over 1,000. I'm gonna repeat it. Are we having fun yet? All right, so some things we need to know. Our degrees of freedom for this test are going to be R minus 1 times C minus 1, where R equals the number of rows and C equals the number of columns. So be careful when you're doing this. Don't include the totals that we came up with when we did this. So in this case, we've got 4 columns, not 5, don't include the totals, and 3 rows, not 4. So just 4 rows, or 3 rows, 4 columns. So our test statistic is chi-squared, which, remember, the chi-squared is just, and now we have to do it for each entry, the observed minus the expected squared over the expected. So we would start off with 68 from our observed minus 88.665 squared over 80.665 plus a bunch of other stuff plus 52 is our observed. We multiply this bottom right entry out. What we end up getting is 38.925 squared over 38.925, and this is going to roughly be 34.638. Okay, so what does that give us then? Well, what we can do is we can do our p-value test. I'm out of room, so I'm only going to do the p-value test. Here, what we're looking at is a chi-squared CDF of 34.638. Our upper bound is infinity, and our degrees of freedom is the number of rows minus 1, so 2, times the number of columns minus 1, so 3, so it'll be 6. And so let's go ahead and put that in. Let's put in the chi-squared CDF. So go to our distributions, find chi-squared CDF, put in 34.638, E9, and 6. We get roughly 5.06 times 10 to the negative 6. So that tells us we can reject the null hypothesis. Remember, the null hypothesis here was that the number of majors, or the number of hours studying per week, and the major you chose were independent. And so this is enough for us to reject that idea, even with our very low level of alpha. Now, I know what you're wondering, man, Mr. Smith really just kind of yada-yada'd in the middle there and didn't go ahead and calculate all 12 of these because Mr. Smith really did not want to. And if Mr. Smith doesn't want to, why should I be expected to do that? Well, that's a great question, kids. And so what I'm going to do is I'm going to show you how to use a different one of our tests in order to go ahead and use this. So remember how in the last video we went to the stat menu and we went to chi-squared goodness of fit. And I said, you really use chi-squared goodness of fit and those lists. Well, this time around we're going to go to the chi-squared tests. And so now what we're going to do is, because we're using contingency tables, we want to put our observed and expected in matrices. So if you don't know how to use matrices, it's really easy. I'll show you. What we're going to do is right above this x to the negative 1 is the word matrix. So we'll go second matrix, and then we've got all these different names, and we can do a bunch of things with matrices. If you haven't taken linear algebra, you really ought to take linear algebra. Get to do all the fun things with matrices. It's going to be a great time. Hope to see you there. In the meantime, though, what we want to do is we want to go to edit. So I'm going to go ahead and edit this matrix A. It's got 3 rows, 4 columns, and what we're going to do is we're going to take our observed and put it in there. So I've already done this, so to show you guys for the first time, I'm going to change things up, make it a 1 by 1, and then you can change your number of rows with the first one, so we want 3 rows, and your number of columns with the next one, we want 4 columns, and then in each entry you can go ahead and put in the things you need to. So 68, hit enter, puts me to the right, 106, 131, 40, 119, 103, 127, 81, 70, 52, 51, and 52. Now the next thing you want to do is you want to go to your matrix B and put in your expecteds. Now I've already done this, and I don't know that you have to, so I'm going to experiment with this a little bit at the end, so be patient with me after we've gone through this part of the example. Now what you want to do is you want to go to stat and actually calculate this test. So go to the chi-squared test, got our observed, got our expected, and then we'll go to calculate. And what it does is it'll spit out our chi-squared value, which if we go to where we were, this does give us the thing we thought we had, so 34.638 approximately. It gives us our p-value that we found of 5.06 times 10 to the negative 6, and then it tells us our degrees of freedom. So in case we had forgotten how to calculate that, it'll go ahead and just give that to us, which is great. So that's the chi-squared test on the calculator. It does a lot of this work for us and makes our lives easier. Now I think there might be a way to get around calculating the expecteds. So let me clear this output. And what I want to do is, to test this, I want to make B a 1 by 1 matrix with a 0 in it. Now what I think happens when you use the chi-squared, if my memory serves, is if you tell it that you want to use A and B, and you've got, let me just refresh ourselves here, we've got these observed values in this matrix A. What I think is going to happen is if we tell it B and we calculate, it's still going to do the calculation for us knowing what A is. So the thing that the program on here is using as input is really that matrix A. But since we didn't make matrix B all those expecteds, what it's going to spit out for us, we'll see, earlier it was a 1 by 1, now it's changed. But now it'll go ahead and calculate the expecteds for us as well, so that we don't have to do all of this extra work that we just did, calculating those expected values, which is great. That makes our lives a lot easier if we don't have to do that. So let's walk through the process for computing a test for independence. First, always first, is we have to state our null and alternative hypothesis. The null hypothesis is always going to be that the row and column variables are independent, and then the alternative is always going to say that they are dependent. From here, we need to go ahead and compute our expected values by using the row and column totals and the grand total. So the expected will always be row total times column total divided by grand total. Now from there, our chi-squared statistic is going to be summing up over every possible value of observed minus expected quantity squared divided by the expected. Our degrees of freedom comes from the number of rows minus 1 times the number of columns minus 1. And again, we don't include those total columns. And then we can calculate either by using the p-value and using chi-squared CDF, or by using the critical value and using the table of chi-squared values. Remember this from the last video that we had in order to use that. So this test is always going to be right-tailed because larger values of the test statistic indicate larger differences between our observed and expected values, and that's what's going to give us stronger evidence against the null hypothesis. All right, so that was an example then of testing for independence. And the other thing we have that follows the exact same testing strategy is testing for homogeneity. So the individuals in the previous contingency table were sampled all from the same population. For each individual, the values of both the row and column variables were randomly assigned. In some cases, the values of one variable are going to be assigned by an investigator and aren't random. So what we're going to do is suppose the row variables are assigned. Then each row is a separate population. What we want to do is test if the distribution of the column variables, the column variable, is the same for each row. All right, so let's take a look at an example. We've got two drugs. I'm going to call them Telmis and Rampril, because I don't want to pronounce these drugs the entire time. So we got these two drugs. Maybe I'll just call them T and R. So T and R are designed to reduce high blood pressure. In a clinical trial to compare the effectiveness of these drugs in preventing heart attacks, 25,260 patients, I'm going to underline that, we might need that later, were divided into three groups. One group took a T tablet each day, and another one took an R tablet each day, and the third group took one tablet of each drug each day. Patients were then followed along for 56 months, and the numbers who suffered fatal and non-fatal heart attacks were counted with the following results. So we got these two drugs and both drugs as the possibilities, and what we want to know is whether or not it mattered which grouping we were in. So in this case, the patients were assigned to one of these three categories, and so the only thing that's random distribution of outcomes. You know, having a heart attack that's fatal versus non-fatal versus none is the same for all drug treatment plans. The alternative is that the distribution is not the same and that it's different for at least one of them. So again, we want to go ahead and get our expecteds. So we've got tell, we've got RAM, we've got both. We've got our fatal versus non-fatal versus no heart attack. And so what we can do is we can figure out what our totals are and multiply by the row total times the column total and divide by the grand total as we did before. Or what we can do is we can go ahead and use what we have from our calculator. So if we wanted to fill out this expectation table, kind of a quick and easy way, what we'll do is we'll create a 3x3 matrix, so 3 rows, 3 columns, and we'll fill in the numbers that we have here. So 598, 431, 7,513, 603, 400, 7573, and 620, 424, and 7458. So we have now this table that has what our values were. And we can go ahead and we can do our stat chi-squared test, observe. We don't have the, it'll spit out the expected in the matrix B. We'll go ahead and calculate. And so we're told that our chi-squared value is 2.259 approximately. Before we go ahead and calculate it all, our p-value is going to be 0.688, and our degrees of freedom is 4. Makes sense, we have 3 rows, 3 columns, so minus 2 times 3 minus 2, 2 times 2, or sorry, 3 minus 1, 3 times 3 minus 1 is 2 times 2, which is 4. But we also can go ahead and go to this matrix B and spit it out, and it'll tell us what these values are. So I'm going to round a little bit. So we've got in the first column 607.14, 609.56, 604.30. Next column is 418.43, 420.10, 416.47, and then in the last column we've got 7516.43, 7546.34, and 7481.23. So this is what we would expect the numbers to be based on everything being equally weighted. And so let's talk about what that means for a second. What it means is that we didn't have the same number of total people in each of these different groups that we were looking at. And so we wouldn't expect them to have the exact same number of fatal, exact same number of non-fatal, and exact same number of none. They're going to be a little bit different, but that's just based on how many total we had. And so if we wanted to use this to calculate our chi-squared, remember what we're doing is the observed minus expected, so we would need to know those. So what we're doing is we're taking our test statistic, which is chi-squared, is just 598 minus its expected, which we said was 607.14 squared over 607.14 plus all the other values in between, plus going all the way to the bottom right corner, 7,458 minus 7,481.23 squared over 7,481.23, which is turns out approximately equal to 2.259. And so we already said that our p-value is going to end up being 0.688. So because this is way larger than our value for alpha, what this tells us is that we will fail to reject H naught. What does that tell us then in kind of non-mathy terms? It means that there's not enough evidence to conclude that the distributions are different for each of the drug treatments. Or in other words, what that means is that none of the plans or none of the medicines, either on their own or combined, are necessarily better than the other, or even better than using them both together. Which is maybe a good thing and maybe it's a bad thing, right? If they're more effective together, that would have been something that would have been worth noting. That would have been something very good. But right now, we don't know that there's a reason for one over the other. So on one hand, it doesn't matter which one you take. What would be nice is if we could also include, say, a control group in here that isn't taking any of the drugs, and kind of check against them. However, if you're somebody who has heart issues and is maybe taking one of these two drugs, you're probably not going to want to be told you're signed up for a control group. So this is how we would go ahead and use the chi-squared tests for independence and homogeneity. Once we finish this video now, you're ready to go and tackle both worksheet 10 and the last homework assignment. So when you have a chance, go ahead and start playing around with those.